Hi, everyone. Today I'll be presenting some joint work with Tim Hunter and Laurel Perkins on computationally modeling extralinguistic cognitive constraints on children's sentence processing. To start, I'll ask you to think about the sentence, "Put the frog on the napkin in the box." When hearing this sentence and being presented with a scene like this one here, adults first look at the frog, then to the napkin in the bottom corner. This is because sentence processing is incremental and predictive, so the napkin is initially interpreted as the destination for the frog. But as the rest of the sentence unfolds, their eye gaze returns to the frog and then moves to the box before they act it out correctly. So although incremental processing initially leads adults to the wrong interpretation that the napkin is the destination for the frog, they are able to revise that early interpretation and interpret the sentence correctly. But unlike adults, 5-year-old children appear to be unable to revise from that initial interpretation. In the seminal Trueswell et al. 1999 study, children were presented with the same scene and sentence. Just like adults, they initially interpreted the napkin as the destination for the frog, glancing at the napkin. But unlike adults, they then glanced back at the frog before carrying out an action compatible with that initial interpretation. This effect was coined the kindergarten path effect. Children's performance with the disambiguated sentence, "Put the frog that is on the napkin," is importantly adult-like, suggesting that their performance is specific to the fact that sentence 1 is locally ambiguous, whereas sentence 2 is not. The Trueswell study is consistent with a wide range of other studies showing that although children appear to be unable to revise that children appear to be unable to revise from initial commitments during parsing, which highlights a key difference between child and adult parsing. So what could explain these differences? One possibility is that the extralinguistic cognitive systems that are recruited during sentence processing are still developing in children. Two such systems are working memory and cognitive control. Children's working memory capacity is limited compared to that of adults, so this immature system could potentially constrain the ability to maintain parses that aren't initially preferred in ways that allow you to return to them when that initial guess turns out to be wrong. On the other hand, cognitive control, which is responsible for inhibiting initial responses, takes a notoriously long time to develop. Anyone who's interacted with young children know that they occasionally, or maybe not so occasionally, struggle to control their impulses. With respect to parsing, an immature cognitive control system could potentially impair the ability to move away from a previously high-ranking parse when incompatible information is encountered. Working memory restrictions on parsing have previously been computationally modeled as a restricted capacity beam search by Jurafsky in 1996. In this model, a parameter k encodes the restrictiveness of the memory buffer, or beam. Changes in that parameter over development are one way that you can imagine accounting for the kindergarten path effect. But how could we computationally model the influence of cognitive control on parsing? We propose that cognitive control throughout development could be modeled by allowing the score of an analysis at any point in the parse to be affected by how high or low it previously scored. In other words, the scores for any given analysis would lag in updating, such that novel information is not immediately incorporated. We implement this with a weighting parameter W, which applies to the previous score of that analysis. The goal of this study is to develop a computational parser with 2 independently modifiable parameters, which can model development of each system. We aim to capture the difference between children and adults in that seminal Trueswell study by individually adjusting each parameter in order to independently probe the effects of development in both cognitive systems on parsing. And as a findings sneak peek, we find that limitations in either system, or a combination of both systems, could be responsible for children's performance in this experiment. But critically, we find that the different systems make distinct empirical predictions for an interpretation of the target sentence that was not considered in that experiment. So now I'll give an overview of the computational parser that we developed and implemented for this study. I'll start with an intuitive explanation of the critical choice points faced by a left corner parser while parsing the test sentence, "Put the frog on the napkin in the box." At the point where put and the frog have been heard, the parser will have constructed this tree, which has a predicted NP for the object to be moved and a PP for the destination. Now, for the purposes of this demonstration, all of the scores on this slide are just imagined and aren't super important at the moment, although they'll come in later to inform parsing decisions. So let's say at this point, this tree has earned a score of, let's say, 0.54. The next step is how to incorporate the frog. There are two possible choices here. In both cases, the frog is being assembled into an NP. The critical question is whether this NP has already been predicted, as in option A here, or whether it's a different NP node, as in option B here. Our parser pursues the top scoring candidate first in a form of limited parallelism. At each point in the parser compares the scores of the candidates on the beam and pursues the top scoring candidate. So now, continuing with option A, we see the word on. The predicted NP, the frog, has already been fully filled out, so this will be part of the goal PP. Then, after hearing the napkin, all of the predicted arguments of put will now have been filled. So then, when you hear the word in, there's nowhere to put it in option A, making this parse no longer viable, the kindergarten path. So the parser would now switch back to pursuing option B, back to considering where to incorporate on. In option B, we've left open the possibility that the predicted theme NP is going to be much bigger. So on becomes part of the NP modifier of the frog. And once you hear the napkin, this has filled in the modifier NP. Now, when the word in is encountered, there's still the goal PP argument left to be filled in option B. So it's perfectly compatible with being part of that predicted goal. We're going to explain the difference between children and adults as a difference in their ability to make that switch to option B when option A is no longer viable. We'll think about this in two ways. One way that models working memory constraints, and one way that models an additional constraint on cognitive control. Here's the way garden paths have previously been modeled in adults, for example, by Jarafsky in 1996. Scores are subject to a threshold corresponding to working memory, K. A garden path occurs because the intended analysis falls off of the beam because it failed to meet that threshold K at some point. So here's the initial choice point we considered before. But now, if we want to model children's restrictions on memory capacity that could result in kindergarten pathing, we could compare the ratio of these scores to a memory threshold, K. K is essentially the limit on how disparate these scores can be. So here's our ratio of scores, which in this case happens to be lower than K. As a result, option B would be lost from the beam at this point, and that means that only option A would be maintained and pursued like this. And because option B was lost because it dipped below that K threshold, the intended analysis is never found because it's not available to be returned to. Meanwhile, in an adult-like system with a low K threshold, the parse would proceed, as in the example we saw on them previously, switching to B when A was no longer an option. So this could be one explanation for the kindergarten path effect. Perhaps differences between children's and adults' working memory could explain differences in their parsing. Perhaps the difference is the setting of this threshold requirement, K, which changes over time as children develop. The other possibility is that it's not that K changes, but that the scores going into the threshold computation are different for children versus adults, reflecting differences in cognitive control. We model this here through a parameter that gives some weight to how good an analysis was before the most recent step of parsing. We implement that as a weighted geometric average, which applies some weight, W, to the previous score of the analysis, 0.54 here, in addition to the raw score that this candidate would otherwise earn, to yield a weighted score. So in the case of option A here, the weighted score that's considered by the parser would be the weighted geometric mean of the previous score, 0.54, with the raw score of this step, 0.79. But because in this example we're putting some weight W on the previous score, the weighted score will only be 0.62. Essentially, there's a lag in updating that score, even though this is a pretty good option. And in the case of B here, although the raw score of that step is really bad at 0.07, the weighted score would cushion that drop to only 0.13. As before, the parser will pursue the higher scoring candidate first, and each of these steps is looking pretty good, so the score has now leveled out at around 0.96. But critically, for option B to remain on the beam, it has to pass the K threshold at each step, And unfortunately, at this point, because option A looks so good now, option B doesn't meet that threshold for K, even if it's set to a low adult-like K setting. So even though the disparity at that initial choice point wasn't as big and it was able to stick around, now that option A has been pursued and has achieved a high score, option B will be lost. And when the parser continues with option A, it encounters the word in and has no way to incorporate it because all of the arguments have already been filled. And because option B was lost just one step before, the dreaded kindergarten path strikes again. And because that intended analysis cannot be pursued, even though the disparity in scores at that initial choice point was nowhere near as big as it would have been without waiting. So another possibility we propose is that if children differ from adults, not in the threshold requirement, or K, but in the scores they actually assign to these analyses, could this also explain the kindergarten path effect? Could we capture the same empirical results if we had a different way of assigning scores, but held K the same as that of adults? This is what we propose cognitive control may actually be doing. So to summarize, our parser has two relevant parameters that can be modified independently. One is K, which corresponds to a working memory threshold, as in Jurafsky's original model. The other is W, which corresponds to cognitive control's allocation of working memory. And we will use this parser to tease apart whether differences in children's and adults' parsing is the result of changes in that threshold over development, or if it's the result of scoring the analyses differently as a result of cognitive control impeding score updating. And for those of you who are more technically inclined, our parser is a generalized left corner probabilistic beam search parser. Scores are normalized by the number of completed nodes, and it incorporates a one-word look-ahead. The parser was run on a PCFG based on distributions in child-directed speech and incorporated lexical information on the verb level. So we conducted two simulations. In simulation 1, we tested the two sentences and interpretations that were previously studied in Shrewsbury et al. 1999. And in simulation 2, we tested an additional interpretation of the target sentence that hasn't previously been examined. So the desired behavior for our parser is that we should be able to find the intended analysis for both the temporarily ambiguous sentence 1 here and the unambiguous sentence 2 when it's set to adult-like settings of either parameter. But when set to child-like settings, we should no longer be able to find a parse for the ambiguous sentence. And drum roll, please. Here's what we found. First, our parser was able to find the intended analysis of the unambiguous sentence at all values of parameters K and W. So going forward, I'll just be focusing on that temporarily ambiguous sentence. For the temporarily ambiguous sentence, I'll start by showing you the results of varying just K, similar to that original Jurafsky model. Higher values of K correspond to a more restricted memory, also known as a higher threshold, as we might expect in children. Lower values of K correspond to less restricted memory as a lower threshold, as might be expected in adults. We have two colored regions here, which indicate whether or not the analysis was found, with blue meaning none, and yellow meaning that it was found. We see that at more restricted settings of our working memory parameter, no analysis is found for the ambiguous test sentence. But at less restrictive settings of that parameter, the intended parse is found. This isn't very surprising. This is what we would expect. But now, if we add in a little bit of score updating through our parameter W, where lower values of W indicate faster score updating, like we would expect in adults, and higher values of W correspond to a lag in score updating, like we would expect in children, we see the same overall trajectory for pretty much all values of W. So we see here that adding in that score updating can also account for the empirical data. For example, if we only consider a change in working memory, varying K from high to low while keeping W small, just like this, we get the same trajectory as if we kept K small and relatively unrestricted while only considering a change in cognitive control, W. And we even see the same thing if you allow both to vary simultaneously, like this. So pretty much any way you slice it, you get the same trajectory, a period of not finding the analysis, followed by one where it's found, capturing the original experimental results. So in summary, in simulation 1, our parser showed that children's and adults' performances on the standard interpretation of the test sentence can be explained by either developing working memory, developing cognitive control, or a combination of both. But the empirical data from the original study won't help us tease apart these two systems, which one is primarily responsible for differences between child and adult parsing. So where should we turn to tease them apart? Well, here's a possibility. The test sentence is globally ambiguous. You could either interpret it as originally intended in the experiment, such that the frog is on the napkin and is to be moved into the box like this, or you can interpret it as in the tree on the right, such that the frog is to be placed onto the napkin, which is already in the box, like this. But in the original experiment, there was no napkin in the box. So even if children could access this other interpretation, there was no way for them to show it. This gives us a new test case for our parser that may tease apart the possibilities. In our previous simulation, we weren't looking at this interpretation, so in simulation 2, we're going to look at what happens when the parser can entertain this possibility. So I'm going to present you with a very similar figure as we saw before, but now you'll notice that we have a new color. The blue region corresponds to the alternative napkin in the box analysis. The yellow region corresponds to areas where only the originally intended analysis is found, where the frog is on the napkin, and the green corresponds to where both analyses are found. And what we see is that if we have immediate score updating and only consider working memory, or K, we have 3 distinct phases. At the most restrictive settings of K, only the napkin in the box analysis is found. At the middle ranges of K, a new phase where only the intended analysis is found. And finally, as K is least restricted, both analyses are found. So would the same pattern be predicted if we begin to incorporate cognitive control or a lag in score updating? So again, we have W here on the x-axis, and here's what we find. We actually see a different pattern emerge. So once W is in any way incorporated, we now see transitions between only 2 regions, the blue napkin in the box only analysis, and the green region where both the intended frog on the napkin and the napkin in the box analysis are found. Remember that on one hypothesis, the difference between child and adult parsing is a result of working memory threshold changing throughout development. So on this graph, that would mean just moving along the y-axis here at the smallest values of W. And what we see there is a 3-stage development between these analyses. But on another hypothesis, the difference between child and adult parsing is the result of differences in how cognitive control influences parsing. On this graph, that would mean moving just along the x-axis at the smallest, least restricted values of K. In other words, if score updating is even a little bit lagging, we no longer will have a phase when only the intended analysis can be accessed and not the alternative. And that holds even if you approach on the diagonal, meaning that you're allowing both to vary simultaneously. There's still just a 2-stage trajectory. So simulation 2 has made a key empirical prediction here that can help us distinguish the influence that changes in these 2 systems can have on parsing throughout development. If changes in working memory throughout development are primarily responsible, we expect to see a 3-stage developmental trajectory where the alternative analysis, intended analysis, and both analyses can be accessed at different points in development. But if changes in cognitive control contribute at all, we would expect to see a 2-stage developmental trajectory where at less mature stages, only the alternative can be accessed, followed by a period when both can be accessed. These predictions haven't been tested yet, but could be tested experimentally if someone would like to do so. We have some ideas, so feel free to ask us during the question period or after this session. So to summarize, in this study, we proposed one way of formalizing how cognitive control interacts with working memory during parsing throughout development. We implemented an incremental and predictive model of children's parsing on test sentences in Truesdell et al. 1999 and ran 2 simulations. In simulation 1, we looked at the role of cognitive control and working memory development on interpretations of the critical experimental sentence that has previously been tested, and in simulation 2, we considered a previously unexamined interpretation of that test sentence. And it turns out that either hypothesis can predict the results from Truesdell et al. In simulation 1, but they make distinct predictions about a previously unexamined interpretation of that test sentence in simulation 2. So by formalizing these systems, we've revealed one place to look if we want to tease these systems apart experimentally. So this work was generously supported by an NSF DDRI grant, which allowed me to hire an amazing undergraduate research assistant, Shunat Query, who helped me develop a lexicalized PCFG for the parser. And I wanted to thank all of you today for your attention, and I'm happy to take any questions. Hello.
Really great talk. I enjoyed it. Lots of different questions, but I guess I'll try to focus on a couple things here. Just one little side note is that that alternative interpretation has been seen in some of the error actions that you do see, but I believe it's actually only in the adults, oddly. I have to go back and check. Some adults will take the frog and the napkin together and put them in the box, okay? But I don't think, and I have to go back, it's been so long, but I have to go back and check. But I believe the kids never did that kind of analysis. So that's an interesting little data point. But the second thing is just about modeling cognitive control. You've picked a very particular way of doing it that is kind of unusual. I mean, it is sort of more like a hysteresis effect or something, you know, like you're persisting in something. You're just like, I'm gonna do that, and that you become more flexible, I guess, more rapidly updating as you mature. Lots of other alternative ways of modeling cognitive control. Have you tried to do any of those? Like, for instance, the degree to which you might selectively inhibit one or something along that lines, rather than preferentially, you know, not changing, you know, having the weights change more slowly, essentially.
We did not try any other options. We kind of just proposed that this was a way of allocating working memory by kind of having that slow updating as a way of kind of modeling not being able to change course once you've made that commitment, or like at least where a candidate came from as having influence. But it would be interesting to try some of these other ways of modeling cognitive control as well.
And I hope someone asks what your experimental ideas are, but I won't.
Okay. Thank you.
Hi, I'm Christian Clark from Ohio State. I think this is super interesting work. I had a question about your way of modeling working memory. You describe it as the number of elements, I guess, in a parallel parse, in the parse beam, so that like K value, right? I guess one other notion of working memory has to do with the structure of the individual parses, whether they contain center embeddings. So I guess I'm curious if that alternative notion of working memory use that kind of goes back to Chomsky, I think, if that could tie into this at all, or if there would be any way of modeling that idea about working memory.
I'm not sure I'm fully familiar with the type of working memory modeling that you're talking about, but the way that it wasn't quite the number that was restricted in our case, it was a probability threshold essentially.
Okay,
so there could be essentially an unbounded number of parses at any point if they were all close together, like if they were all similarly activated. It was a little bit more of an activation working memory parallel as opposed to like a distinct number. So I think it would probably follow center embedding depending on how those probability disparities come into play.
Yeah, so I mean, I think since you're doing like a left corner parsing, the center embeddings are easy to count just from the number of kind of disjoint fragments in the parser. Yeah, thanks.
Okay, great, thanks.
Hi. My question is going to bounce off of John's. It's very similar, right? Which is, it seems like the trickiest thing about this work, or maybe any kind of modeling work, is drawing some sort of a connection between parameters in your model and the kind of verbal and global theories that other folks have been working with. And I can understand why you've chosen to draw the connections you have, because they stand the best chance of bringing people into the room for a conversation, right? Like there's a whole working group focused on cognitive control and another working group focused on working memory, right? But I'm also a little bit nervous about labeling these parameters in that way. And so one of the things I tried to think to myself is, well, the working group on cognitive control, what have they told me over the years they would take to be evidence for cognitive control? I think it's got to be domain general. It's got to involve being able to look at conflicting cues, right? I'm not seeing that in your parameter. You got a cool parameter that you can move around here and you can look at, right? But I'm not sure it's mapping onto that construct. I'm actually wondering if it's mapping onto maybe a slightly different construct that people have talked about in the more loose and lacy verbal way, right? Which is speed of processing. So if we're thinking about the speed with which you exchange information across different types of representations, this seems like a lag in that updating, right? Which maybe that's more about a continuous growth in neural efficiency than it is about a domain-specific cognitive control mechanism changing over time. Thoughts?
Yeah, that's definitely an interesting thing. This was meant as kind of a first pass, almost like a proof of concept to see how we could begin to incorporate that parameter, but there's obviously different ways that you could think of making it more sophisticated, trying to bring in more, I don't know, referential information in some way, but we just started as a sort of simple starting point, and we thought of it as weighting, but as Truisall said, there's other ways of potentially modeling cognitive control. This is just a starting point and a conversation starter, like you said. So, always good to keep other things in mind. And moving forward, we'll think about other things as well.
Hi, Mary Ellen McDonald, University of Wisconsin. I want to ask a little bit of a similar question to Jesse. I want to ask about the relationship between the way you're setting up the model and the way we think humans might be doing things. And one way I want to ask about is the relationship in humans between their language experience and abilities and their cognitive control and working memory. So you've clearly set up a lovely example of how to treat those separately, but I don't think that's what the data suggests. So for example, in children, their conversational experience correlates with their cognitive control measures. And their vocabulary development at age N correlates with their cognitive control abilities at N plus something else. So the relationship is that what kids are experiencing and what they know about likely interpretations potentially for sentences is varying via their language experience and also driving their cognitive control. So I'm wondering how you might think about, and I can say the same story for a similar story for working memory. So I'm wondering what you see as the costs and benefits of the modeling enterprise in which the language abilities and experiences are completely separate from these other two parameters.
So this is actually something we've thought about to some extent, at least in terms of lexical drivers of prediction and interpretation. So I mentioned that we have a lexicalized PCFG, so they are basing, or the parser is basing its steps on the probabilities of the argument structures for those verbs, because we know that young infants use those types of probabilities for known vocabulary words to guide their parsing and to guide their interpretations. So we've begun to think about this, but I think the initial motivation for this project was that it's really hard to tease apart these systems and language exposure and language knowledge. So we were trying to formalize it in a way just to start being able to tease apart the distinction between those two, because it's not always obvious and it's not easy to get at whether it's the extralinguistic cognitive systems that are driving, language performance or vice versa. And so this was a first step in that direction, but something that we could do and something that we've thought about doing in the future is incorporating more ways of modeling a child's language knowledge in addition to these parameters developing in time. So making like pseudo verbs that you don't know what the distribution, typical distribution of their arguments is in language, so you would interpret it differently. Sorry, I feel like I dwindled off there. But yes, that's something that we would want to consider in future work, and this was an initial attempt at formalizing those systems.
Hi, Al Kim, University of Colorado. I want to ask another question going back to, ask you about what your model is modeling. And you're framing it in a non-mechanistic way, sort of talking about probabilities and having a threshold beyond which, some representation will be lost. But as I think about your drawing with two parse tree paths developing and then one gets cut off when your ratio falls below a certain level, I'm sort of can't help but want to turn that into a mechanistic model and thinking about holding two representations simultaneously in mind. And is that something that you're willing to posit? Is that, you know, and if so, is that something that you could measure? Like, is the demand on working memory, is it one of like holding, when you think about working memory, are you thinking about holding two parses, two interpretations simultaneously in your mind and having trouble simultaneously holding those two things? Is that what your model is saying, or is it definitely not what your model is saying? And if there were such a burden, would you be able to measure it?
I think to some extent that is what our model is modeling here. So having, it's maybe I'm having a little bit of trouble kind of formulating this, but the strain is kind of keeping these different analyses alive when they might have disparate probabilities. So that is, in some sense, the way that the working memory system is being strained. So I don't know if that answers your question, but I think, yes, we are modeling working memory in that way.
Awesome. Let's thank our speaker.